Log on, tune in, find out. Another good idea from Cambridge.
Thanks. Thanks again for the invitation. So as you're probably aware by now, this is joint work with nets. Okay, so I want to tell you the goal for today, and that is to describe the structure of additively non-smoothing sets. So remember that additively non-smoothing sets arose in our study of the density of cap sets in F3 to the n. Everything I say today doesn't really have anything to do with cap sets anymore. So this problem can be considered independently, which is what I'm going to do. However, I will keep all of the same numerology from the previous talks in case any of you actually remember it. Okay, so I'll also remind you what it means to be non-smoothing. So this is the L4 norm of the Fourier transform of the set delta, and it has to do with the number of additive 4 tuples in the set, and it's of course controlled by raised to some power, raised to some other power, and this tells us that the number of additive 8 tuples in our set is bigger than the number of 4 tuples raised to the third power. Okay, so in the cap set world, we had e to the 8, or e8, bigger than n to the 7th cubed divided by n to the third squared, which is equal to n to the 15th. And in fact, we knew that this was less than n to the 15th plus sigma. Okay, that's the end of the review. So what a non-smoothing set is a set delta such that the number of additive 8 tuples is trapped between whatever trivial bound we get from here and some slightly larger number. So here comes the theorem. This is just, there's no reason why I'm taking this to the end of the third other than that it makes the numerology work with the previous talks. Similarly with this assumption on the energy. And just remember that E4 is the number of additive 4 tuples in the set, and E8 is the number of additive 8 tuples. And the claim is then there exists some parameter and disjoint sets B1 through Bn to the alpha. All of them are in delta. And then the claim is that each one of these Bj's has a lot of structure. So the set delta gets divided into n to the alpha pieces, each one of which is going to have a lot of structure, and I'll tell you exactly what I mean by that. Each Bj has a subset, a large subset, which will essentially stabilize the set Bj. So E of two sets x and y is the number of the set of x1, x2, y1, y2, such that x1 minus x2 is equal to y1 minus y2. It's essentially the notion of additive energy as used here, except it's for two different sets. And I'll point out that this is the maximal possible number for, without that error, the size of the small set squared times the size of the large set is the maximal number of 4 tuples that a pair of sets can have. Because if I take, let's say it's like this, I can take an x1 arbitrary and an x2 arbitrary, and then y1 arbitrary, and then the last guy is fixed. So at most, size x times size y choices. And then if I use the asymmetric Balog-Simonetti-Gowers theorem, for example, I can then conclude that the set Bj is actually sort of morally equal to Cj plus a bunch of translates of Cj. Any questions about the theorem so far? So Netz actually, Netz proved this theorem. Netz showed that if certain conditions work out well, then we can take alpha to be 0, and in that case, he established this fact. So I'm going to consider the other cases. Okay, so if I had had this sum be over all x in the different set delta minus delta, then this expression is just the additive energy. It's the number of 4 tuples. And what I'm claiming is that I can restrict to subset D here that gives me all of the energy up to some logarithmic error, and such that this number is constant for D and D. And this number alpha is going to be the same as that number alpha over there. So notice that in this situation we have size of D times n to the 1 plus alpha squared is equal to essentially n to the 7th. So this implies that size D is equal to n to the 5 minus 2 alpha. Okay, that number is going to be helpful for us. Okay, so here's a bit of notation that was introduced earlier. So actually, I guess this is the same as delta intersected with x plus delta. No, that's the set. So maybe that's this different set D comes from a certain graph of pairs. So let G sub alpha be the set of all pairs A and B in delta squared, such that A minus B is in D. Well, I could have put a subscript alpha on there, but I didn't. And the size of this graph is equal to the size of that different set times n to the 1 plus alpha, because for every element of this different set, there are n to the 1 plus alpha, many ways of writing it. So the size of the graph is equal to that. N to the 6 minus alpha. 5 minus 2 alpha, 1 plus alpha. So that's that. Okay, so the reason I'm bothering to write this down is that any given atypical element in delta will have n to the 3 minus alpha b such that a, b is in the graph. So somehow A is friendly with this many other elements of the set. And when alpha is equal to 0, that means that a typical element is friendly with everybody else in the set. And that was one reason why the alpha equals 0 case is a little bit easier. Okay. And I also mentioned this because I'm now going to do a computation that requires us to know that number. The sum may come a little bit out of the blue, although if you've seen the previous talks, then you've seen the sum before. So we can profit, so remember delta bracket x is the set here, and we can profit by looking at how these sets delta bracket x behave with respect to other sets delta bracket y for different elements of the different set. So first off, I'm going to put a lower bound on this sum, and then I'll make some other comments about it. So if I have an element that is in both of those sets, and let's call it A, that means that A minus x is in delta, some B, and then A minus y is also in delta. We get some C. Okay, so the way I have it written, I'm summing over x and summing over y, but this is the same as summing over all points and adding up the number of x such that x is in, such that A is in delta x squared. And what I told you before was that the number of friends that A has is typically that many. So this is bigger than the size of delta times n to the 3 minus alpha squared, and that's n to the 9 minus 2 alpha. Okay, sort of a magic number so far, but anyway, this thing is bigger than this thing. Now, we're going to start keeping track of what this number is. After some pigeonholing, we can assume that it's approximately n to the beta for some value of beta. Does anybody want to ask a question? Okay, so by pigeonholing we find some beta, and then we actually can restrict our sum here to a set of all x and y in a certain set of pairs such that this number is equal to n to the beta. Okay, so the definition is if beta is bigger than, or if beta is almost 1 plus alpha, we say we have comity. Okay, that's slightly imprecise, but it's not so important. Notice that the size of delta bracket x is n to the 1 plus alpha. So if the size of this intersection, the largest it could possibly be, is n to the 1 plus alpha. So beta cannot be any bigger than 1 plus alpha. And we say that we have comedy if it's basically 1 plus alpha. Okay, so here's the set of pairs P. The set of pairs in D cross D where this number is large, meaning that big. So these are the friends of X. And I should say, so until I update you, we're going to assume that we're in the situation where beta is actually equal to 1 plus alpha. So that means that there exists a set of pairs such that delta bracket x is basically equal to delta bracket y. That's what it means to have comedy. So everything I say for a while is going to have some small error terms in it, where the error term is understood to be very small because beta is very close to 1 plus alpha. So in particular, this tells us that for a typical x, if I sum over the y's that it's friends with, I get, for every single one of them, I get a full intersection, which is that number. Okay. So there's going to be a little bit of magic happening pretty soon, so you should all just be on the lookout. So this expression here tells us that for basically all elements in delta x, because this intersection is full, I have that a minus y is in delta. That's because most elements in delta x are also in delta y, so if I subtract off a y, I still land in delta. Okay. Another way of saying this is that most elements in delta x plus an element in f of x give me something that is still in delta. So this, if I just apply the Cauchy-Schwarz inequality, then I get the size of delta, the 1/2, times this other number. And fortunately, this number is equal to the additive energy of delta bracket x with f of x, the friends of x. Now technically, this is a set of differences, but since essentially every element in delta x participates in one of these differences, we should still be thinking of this as being an A. Sorry, being a delta. Does anybody want to make me pause for anything? Okay, so I deleted the theorem, but the claim was there exists some big set B1, and B1 had additive energy with some other set C1 contained in B1. So ideally, this is going to be the set C1, and this is going to be the set B1. But it's not quite what we want unless we have some other hypothesis. So here's a picture of the alpha equals 0 case. I have a bunch of subspace, one subspace that gets translated around at random. So here's some x, and here's some y, here's a z. So if this is x, then y, z, and w are friends of x, because the guys that participate in differences like x are also the ones that participate in differences like y. But if this is q, q is not a friend of x, because the people who are translated by a difference of q are not also translated by a difference of x. Okay, so f of x, the friends of x, is just, notice that it's this guy, this guy, this guy, this guy, which looks an awful lot like a copy of the entire set. So when alpha is equal to 0, it actually is a copy of the entire set. So right, so all of this implies that the energy of delta bracket x with this other thing, friends of x, that's bigger than size f of x squared n to the 2 plus 2 alpha divided by the size of delta. So if alpha is equal to 0, then the size of the friends of x is equal to n to the 3. In general, which of course is equal to the size of delta. Because every element in A has this many friends. So what I've shown is that if alpha is equal to 0, then size of delta is equal to this thing here. So in that case, we would have because this thing here is that thing there. And that would be the claim about the energy that we want to define. So this would be our C, and this would be our B. Now the problem is that, in general, alpha is not equal to 0. This could be fixed if what if the sum were over a smaller set, like some copy of f of x? So what that would look like in this picture is, suppose that we had some other subspace pointed in a different direction, and our set was now made up of these subspaces plus these other ones pointed in a different direction. Somehow, it's conceivable that we need the sum to go over all elements, so that when we take an element here and we move it by x, we stay in the same color. That would be ideal, but it's conceivable that it goes into the purple. So that's why we need a summation over delta here in general, but we would like to have that. So if I can restrict the sum, that means that I'll be able to partition the set into big pieces like that. So I'm now going to introduce a definition that sort of captures when that's possible and when it's not. So what we really want, we would like to be able to restrict the sum to being over a smaller set, but there's a different way to say that. Here I didn't write it over a smaller sum, but you should just imagine that that's happening. What I really want is that the L2 norm of this expression is large, because that was the energy that I was looking for. So then I'm going to now take this expression and turn it into another expression that looks very familiar, and then give you a definition. So I guess I should say that all of this discussion sort of happened. I fixed x, and I defined this object, and then the rest of this discussion took place for a typical x. So I'm now going to count all x's in the different set. So there's a square there, and there's not a square there. So this is the thing I want to estimate, but this is the thing that I already understand. So if I have an element in here, then it's like an A is equal to D plus some Y in here. So that means that the inner expression is just this. But now I'm going to, well, so I push the sum over D inside, and I get back this expression, which we've seen before. The people who participate in X and the people who participate in a Y. And we already saw that this number was whatever that happens to be. It's some number that we know about. So the point of all this is I have this expression whose L1 norm I have good control on, and I want to know what its L2 norm is. Sort of like at one point we knew the L1 norm of this expression, and we wanted to know whether these numbers were large or small. So I'm now going to pigeonhole again to find a level set of these guys from n to the gamma. And I now have a set of pairs Q such that the sum over X and D and Q of that thing, which happens to be size n to the gamma, is still essentially whatever that number was. And once again, this number is bounded above by n to the 1 plus alpha, because that's the size of that set here. So let's just make a definition. If gamma is essentially then we have sideways comedy. So comedy measures this, which was n to the beta, and we have comedy when this L2 norm, well, when the L2 norm of this thing is essentially maximal, and we have sideways comedy when the L2 norm of this version of it is essentially maximal. And what I showed over here was that if this L2 norm is essentially maximal, then basically by definition, we have that the energy of a big piece of the set is maximal. And maybe if you're really, really awake, you notice that I haven't really said anything about comedy for a while, but it's in the background because all of my estimates and my claims sort of had little errors in them, which depended on the comedy to start with.
Am I right in saying that we've yet to use the upper bound on the additive base energy?
You were right to say that.
We're going to, I see.
Yes. So maybe I'll step back and give a bigger picture. We have these two parameters, comedy and sideways comedy. For the moment, I've assumed that they're both remarkably good. In that situation, we have already found the structure that we desire to find, which is namely one of these different sets has been translated around. And alpha was established long ago. The set delta breaks into the alpha different pieces to which I might apply this argument. Okay, so now if we're in the undesirable situation that the comedy is not optimal, or the sideways comedy is not optimal, we have to do something different, and I'm going to discuss that now. So there are essentially two options. One is that the comedy parameter is not optimal, and one is that the sideways comedy parameter is not optimal. And if the comedy parameter is not optimal, we'll use this assumption that Ben is mentioning, namely that we have control on the number of octuples in the set. So, fortunately I erased that, so what if we don't have comedy? So remember that we had this parameter alpha, which is, I'm going to call the height. We have some parameter called alpha, and the size of this graph of differences was n to the 6 minus alpha, just for the record. Well, since this graph of differences is, of course, contained in delta minus delta, we know that the size of the graph is less than n to the 6th, which implies that alpha is bigger than 0. Okay, that's not really so important, except that the structure of the argument is going to be, suppose we don't have the comedy parameter that we desire, then I chose the wrong alpha. Then I can find a different set with a different alpha that gives me all of the energy. So remember we had delta controlled as delta intersected with x plus delta for x and some d alpha. We had bigger than 7. So if we have non-optimal comedy, then there exists some alpha, which is noticeably, some alpha prime, which is noticeably less than alpha, say less than some function of the smoothing parameter sigma, such that, in fact, we could have summed over x in this different set of alpha prime and still obtained all of this energy. So we should have started at a different place. And now there's some fuzziness happening here. Depending on sigma. So n to the 7. This is what, so Nets would have written n to the 7 minus. Okay, so now I have to tell you why I can find such another d alpha prime. So, I drew this picture before, but here's the expression that reflects comedy. This is the one that has to do with comedy, and this is the one that has to do with sideways comedy. So, I drew this picture already. Suppose I have an A that is in delta x bracket delta y. Then I can subtract x and get another element b which is still in delta. And I can subtract y and get another element c which is still in delta. Okay, so there's that picture. If a is in delta x bracket delta y, there exists a b and c in delta such that x minus y is equal to b minus c. Or maybe it should have been a c minus b, whatever. So if here b is equal to a minus x and c is equal to a minus y. So x minus y is equal to c minus b. But I had a lot of those. I didn't just have one element in that intersection, I had n to the beta. So that means that there are lots of ways So there exists C1, C2, dot, 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 C sub n to the beta, and B1, B2, B sub n to the beta, such that x minus y is equal to Cj minus Bj. Okay, what that means is that delta, well, it means this is n to the beta. Well, I don't really like that way of writing it. So far, so good? There could be more, but there are at least that many, because I've just produced them for you. So here's my B1, or my BJs and my CJs. Okay. Now, that's where we use the size of beta. We also had this other piece of information, which was that this was for x and y in a large set of pairs. And maybe I'll write down the exact size of that set P, but for the moment, let's just not bother with it. So this means that for every element in that set of pairs, I have For every x and y in that set of pairs, I have this property here. That's just copying what I've said before. And another way to think of that is this is in d squared. Summing over all elements in n to the beta, in a different set, which is now a new one. Yikes. For every x and y here, I land, x minus y lands me in some different set, which I'm now calling d prime, where d prime is the set of all d such that is bigger than n to the beta. Okay, and then once again, I'm going to apply Cauchy-Schwarz to get some estimate on the L2 norm of this function, which is the same thing as the energy of the set D sub alpha. So now we're about to talk about 8 tuples. So this is less than or equal to the size of d prime square root times the energy of the number of 4 tuples in that set d alpha square root. Okay, why is this relevant? If the number of 8 tuples in the set delta is at least this number, which I'll explain momentarily. Knowing something about the number of 4 tuples in the different set, d alpha, tells me something about the number of 8 tuples in the set that we started with. So if I have a d1 plus d2, which is equal to d3 plus d4, and each one of these d's can be written as an a1 minus a1 prime, and there are n to the 1 plus alpha many ways of doing that, because each difference in d has a certain number of representatives, namely n to the 1 plus alpha, and so on. And of course, that's an 8 tuple in delta. So that's why I have that estimate there. So here's an expression that gives me a lower bound on the energy of d4, or the energy of d alpha, and here's an upper bound, of course. The upper bound is n to the 15 plus sigma. So notice that that lower bound depends on a couple of things. It depends on the size of d prime, which depends on this number beta, and it also depends on the number of pairs there. So E4 of d alpha is bigger than the number of pairs squared divided by the size of the set that it goes into. And we can compute that. Here we had sizes p, and each one of those contributed an n to the beta. Size of p, n to the beta, is bigger than that number. Okay, this isn't all that important. The point of carrying out this computation is to show you that the parameter beta doesn't actually play a role. So that's equal to n to the 18 minus 4 alpha minus 2 beta divided by the size of d prime. And the size of d prime here, well, we know how many additive quadruples we have, so we have an upper bound too. We know that the size of this d prime is less than or equal to n to the 7th divided by n to the 2 beta, because I have an n to the 7th here, and if each one of these is like an n to the beta, then that's where I get that. So it's less than that. So let's say it's equal to that plus, or maybe it's even a little bit smaller, some parameter delta. Then this is n to the 18 minus 4 alpha minus 2 beta divided by n to the 7 minus 2 beta minus delta. So this is n to the 11 minus 4 alpha plus delta. So the point of all of that computation was to show that if I add to that exponent 4 plus 4 alpha, I get 15. And if I have some extra delta there, because that set was too small, then I get 15 plus delta. But that's too big, unless delta is smaller than sigma. So there's our d prime. Now, let's ask this question. If beta were bigger than 1 plus alpha minus a small error, we already had comity. So what if not?
Can I ask a question that's not directly...
Yes.
I wonder whether there's some graph theory lemma that's basically behind this, because it seems that you're not using all that much about addition. Like, you haven't done any clever rearrangements of additions and things. And if you just look at the weighted graph, which gives the number of ways of writing x minus y as a difference of two elements, there's some essentially graph theoretic lemma of which this is a corollary. Like, in much the same way that Balog-Semredi Gauss is a consequence of a graph theoretic lemma. It's just a suggestion.
I've thought about ways of looking at this in terms of ways of thinking about related things in terms of graph theory. I guess I have to say it depends on exactly which graph you're talking about, because there are some ways of encoding this information into a graph that don't really capture the whole problem. So for example, these x's and y's that we chose all came out of a certain difference set. And so there's some loss by passing to a different set. And just knowing the size of the different set, for example, is not enough information to have in the graph. I mean, that doesn't mean there isn't something else, but that's a good suggestion, I guess.
No, I mean, it's just a bit of an idle suggestion, but it seems as a lot of the manipulations you're doing could be more pleasantly encoded as sort of talking about intersections of neighborhoods and things like this. At least some of them could, but maybe not all of them.
Okay.
Well, there is some rearranging, right? When we get x minus y as a difference.
Which bit there?
So you have an intersection between delta bracket x and delta bracket y, and you conclude that x minus y has conditions. That's something you could addition. Some graph.
Well, but that could be encoded by saying that the neighborhood of x and the neighborhood of y have large overlap. I guess it depends on whether you wanted the elements of your graph to be the elements of the set or the elements of the different set.
Well, I mean, the obvious graph to look at would be the one where you join x to y, and it'll be a weighted graph,
Yeah.
where the weight attached to the edge is the number of representations. That's what...
Well, the weighted graph would actually capture all of the different sets that I mentioned. That's the weight. So I haven't thought about that. Okay, so if this parameter beta were large enough already, then we have some kind of the comity that we wanted. That was the definition of comedy, that beta was, that this number was as large as it could be. So, if not, then what we found is a different set D prime. I guess I got this thing here, such that now this number is n to the beta, and n to the beta is equal to some n to the 1 plus some number smaller than alpha. So there's a new new different set D prime, a new alpha prime with associated different set D alpha prime, which is that one, and then the size of the associated graph is actually equal to n to the 6 minus alpha prime, but alpha prime is now smaller. So that was the big reduction. So we went from alpha to alpha minus some function of the smoothing parameter. And then we're going to iterate it. So next we can go to alpha minus, well, just so my bookkeeping is correct, we may go to a slightly... And the reason I did this is to show that the number of elements in this new different set is really basically as much as it could possibly be. If not, then delta was large and the smoothing assumption was broken. So I claim that what's happened so far is that I've shown that if there's no comedy, then we can fix that problem just by reducing the height. And since the height is above 0, always, we can't do it very many times before we eventually get what we wanted. So my time is running pretty low. I guess I should say something about what happens if we don't have this mysterious sideways comedy that I asked for. Once again, we'll be able to lower the height, but for a different reason. So since I just have a few minutes, I think maybe I'll just finish with an example in which I have a set with sideways comedy and a similar set without sideways comedy, and then I'll point to the way to fix the problem in this particular example and claim that it works in full generality. So here's set A. It's going to be, set delta is going to be a subspace H plus a random set plus another random set. Each has size n. So still have size n to the third. And the set looks something like this. I have one copy of this kind of thing living right here. This is an H plus, say, R2. But then I've got other copies because I'm translating around by R1 as well. So in this example, we can select alpha to be equal to 1. And the different set would be the different set that takes this block to this block and this block to this block. So the different set is equal to H plus R1. And that's example number 1. And I'll give you example number 2, which has the same value of alpha.
You mean H plus R1 minus R1?
Oh yes, thank you. H plus R1 minus R1. So it's a different set of the first random set plus the subspace. So some of you may be noticing that a random set of size n plus a random set of size n looks an awful lot like a random set of size n squared. So here we should be thinking this is h having size n, and then a random set having size n squared. So if you'll forgive me, the size of the blocks is not the same, but this guy has size n, and it's been translated around by a set r, and this set has size n, and it's been, from one perspective, it's been translated around n squared times, and from another perspective, it's been translated around n times here, and then that whole block has been translated around n times by some other set. So if we choose this to be the different set, then alpha equals 1 appears here, because this difference is represented n times n times. And then the other example, I'll have time to draw it for you. And if my time doesn't expire, I'll tell you why, but I claim this one has no sideways comedy. And this next one has, yes, sideways comedy. Delta is equal to the union of a bunch of sets kj, where the size of each one of them is approximately n squared. So this set looks like a bunch of subspaces, all of which are really large, and all of which have no relation to the other ones. So the difference set is just, the popular differences are just going to be the elements inside this subspace together with the elements inside this subspace together with the elements inside the other subspaces. So the difference set is, again, the set we started with. And once again, alpha is equal to 1. And the difference in between these two examples is that if I look at quantities like this, I have that for some x here. Suppose I choose some x in this different set. Then the other elements in the set D that are sort of friendly with it all live inside this subspace. So I get something in this example that looks like all n to the third elements have only n squared friends, and each one of these numbers will therefore be n squared, bringing me up to n to the 7th. And then in this first example, I don't have something like that. So no matter which other element of the set, in this block, or this block, or this block, this piece, there's always an element in h plus r1 minus r1, going like that. So for every pair x and d, in that first example, I get some number here. So the numerology looks more like n to the third, n to the third, and n. Okay, so that's all very quick, but I'm out of time, so I'll stop there.
Oh, well, thank you to both of you for this series of lectures. Are there any questions on the whole, on today or on the whole thing? In a way, I'm kind of glad that it's not obvious that this should combine with Sanders' result, because this would be so nasty.
I'm taking that as a
To
compliment.
take this and do it with 4 sets. It would be very, very hard.
Question.
Yeah.
So today the statement was that if your additive energy is as low as possible, or then you have a good structure. You can partition it into.
The claim on the additive energy is actually not important. It's only the relationship between the 4 tuples and the 8 tuples. So
But there was a structure theorem anyway, so you said that you can partition it into S1,
yeah,
S2, or that those S's have kind of additive structure, yes?
Each one of them, yes.
Each one of them.
Yeah.
But this is true only if it's very close to the extremal, or
Only if the relationship between the 8 tuples and the 4 tuples is very close to the extremal. Extremal in one direction.
but it's not necessarily the case that there's a very small subset.
No,
It's a subset, that's the key, yes. So it's a subset, but smooth. I mean,
it doesn't smooth.
what?
Right. Right. The subset of the subset is as big as it can possibly be given the size of the subset.
Yes. So
So,
it should be interesting itself more.
Actually, I was going to ask a related question, which is, as Nets and I have discussed over many years, these Holder inequalities are basically a poor man's version of Plunker's inequality. So I'm not sure it's quite exactly Plunker's inequality that's being looked at here, but would this give you some sort of structure theorem for when Plunker type inequality is sharp? Presumably it would almost immediately, actually, just by quoting this theorem with the right Plunker type theorem.
I'm a little worried because you could have the size of the subset be as large as it could possibly be, but many of those fourfold sums have not very many representations, and then you don't know very much about the
Yeah, I
energy.
think you need a sort of robust version of Plunker's inequality where you're allowed to drop from A down to A prime, which is maybe a little bit smaller, in which case Plunker becomes better, I think.
I think, I mean, what's the precise statement of Plunker when you talk about the difference set? If it,
Well,
Well, there's a relation between the sort of combinatorial analogue of the additive energy, which is the doubling constant,
Yeah.
and the combinatorial analogue of the number of additive octuples, which is the size of 4A over A.
yeah.
So I don't think those are quite the right things to look at, but some slightly robust version of them. So the PhD thesis of George Petridis, who's the guy who found the new proof of Plunker's inequalities, he did some work on when they're close to sharp, which I don't think it even remotely implies anything like this, but it's probably at least in something like the same direction. Any other remarks? Or maybe we should adjourn for tea. Can we thank these two gentlemen again?